Folks, Merry Christmas if you celebrate Christmas. If not, welcome to December 25th, 2021. The time is here. It is now time to add reaction wheels to my ADCS seminar series video on a CubeSAT full 6DoF quaternion based 6DoF simulation in MATLAB for CubeSats. Right now there are magnetic field model, a gravity model, a magnetorquer model, there's a B-dot controller, there is no reaction wheel model or reaction wheel controller, and so that is what we're going to do in this video. I normally do videos off the cuff. I did kind of cheat on this video and did a little bit of work ahead of time. One of the things is that I haven't looked at this code in a really long time, and so one of the things I did was I cleaned up the code a little bit. So I moved the IGRF model into its parent directory. So there's a directory called ADCS Seminar Series, and then my GitHub called Aerospace. So the IGRF model is in the one before that. I do not push the IGRF DAT files to my repo. So you need to go download that IGRF model on MathWorks, and there's a link here on line 22. I moved all of the IGRF stuff to here. So the magnetic field in the simulation right now updates every second. The planet model is the same. You've got the size of the Earth, the mass of the Earth, the gravitational constant, and then mu, which is g times n. The inertia, this is where things are going to get kind of difficult because we're going to add reaction wheels, and reaction wheels add inertia to the system. And so this is going to be kind of difficult. I haven't done that yet. The initial attitude, right now I'm at 600 kilometers above the surface, 56-degree inclination. And I compute the speed of a circular orbit so that I'm in a perfectly circular orbit around the Earth. My roll, pitch, and yaw are all zeros. I have an initial angular velocity. Right now, I normally compute how many orbits I want to simulate, but the simulation kind of takes a long time, so I'm only simulating for 5 seconds right now. I have a time step of 1 second, which means that the magnetic field model is basically updating every second. I create some empty arrays. I added in the current, so I can plot the current as a function of time. I have a sensor params function here, which basically tells me the noise of all of these sensors. Right now I'm updating the sensors every 5 seconds, which, at least on our CubeSat for South Alabama, for JAGSAT, it's every 10 seconds. And for whatever reason, it still works. We have the satellite dynamics routine. That is in here. I haven't really touched this much. I just kind of looked at it again to make sure I understood that this is where we measure the sensors. This is where we perform our filtering. We compute our control law every time. So this control law is going to need to get edited to compute the reaction wheel speeds. Magnetorquer params, that function or script really, it's just says like the number of turns, the amps, and the max current. So I added in, I moved the saturation filter from the control block to the simulation because the controller can have a saturation filter, but really the dynamics need to have like the end-all be-all saturation filter because the controller can command whatever it wants. Whether or not the dynamics actually can support that, or the current or the circuitry can actually support that, is a completely different beast. And then we've got translational and rotational dynamics, and it's possible we're going to have to edit this rotational dynamics. I'm not entirely sure yet. We will just have to see. In order to add reaction, okay, so let's just run this real quick. So if I run this for 500 seconds, just so you can kind of get an idea of what's going on here, if this is for some reason the first time you're watching this video. Simulation's complete. Plots are supposedly going to be generated. Here's the magnetic field. I added better legends. So the solid lines are the actual values. The squares are the updates. And so, again, the time step is once a second, and I'm measuring a new value every 5 seconds. And so, by the way, since the simulation is running at 1 hertz at 1 second, it means that the control rate is also running at 1 hertz, which is, I guess, okay. The dashed lines are the filter. So you can see that the filter sort of lags behind, and it lags behind because you're running it through a low-pass filter, right? And so it doesn't exactly match up perfectly. So that's the magnetic field from the magnetometer. We have the norm of the magnetic field, which is plotted. I labeled these axes. We have the Euler Angles, which don't really matter because the thing is kind of, the whole satellite's just kind of tumbling. But when we're using reaction wheel control, I mean, we do eventually want to control the satellite to a specific angle. So we'll see if we can do that. Here is the rate gyro measurement. So same thing. The solid lines are the actual values. The values with the squares are the measured. That's the noisy data. And then the dashed lines are the filtered values. And remember, the filtered values are basically the navigation filter, and that's what's going into the control block. Here's the current. And so if you, at any point in time, if you add the current up, the absolute value, it should only equal 120 milliamps, and sure enough, it does. Now, the angular velocity is fast enough, and I didn't point this out, but in the control block, the gain of the control block is huge at 672,000. That's a really big number. And so the current in the magnetorque is just completely saturated, okay? All right, so let's talk about adding reaction wheels. So I have a new book called, I used to have a book called Spaceflight Mechanics, and the book got deprecated. So it is moved to a book called Aerospace Mechanics, and so this is sort of like my holy grail of aerospace. So I have a GitHub repo called LaTeX, and I have some LaTeX textbooks in here. So my old MATLAB textbook is in here, numerical methods, and then I have an instrumentation textbook, which is actually deprecated because it's on Gitbook now. And then aircraft mechanics and spaceflight mechanics also got deprecated and moved into aerospace mechanics. And so the aerospace mechanics textbook right now is only about 60 pages. I have the manuscript changes, different changes that I want to add to the book, and then some acknowledgments. So right now what I'm looking for is this this rigid bodies here. Probably here the reaction wheel model. So here is the reaction wheel model. So this is everything that we need to add in here, right? So we have the inertia of the reaction wheels, and then we have this translation matrix to move us from where this is the reaction wheel inertia in the principal reference frame of the reaction wheel, and then we need to rotate it to the principal axis frame of the satellite. And then we need to use the parallel axis theorem to move the reaction wheel from the center of mass. And then the total inertia is equal to that plus that value there. Now, that's the inertia. The angular momentum, and this is where things get weird, is you have to add not only the inertia of the satellite times the angular velocity of satellite, now you need to add the inertias of the reaction wheels times the angular velocity of each reaction wheel times the unit vector. So every reaction wheel is going to have a unit vector that's pointed in a certain direction. And so we kind of just need to build this up. So what I'm probably going to do, and again, this is the part that's completely on the fly. So let's see, clear, close all. No, CLC. That's what I wanted. I haven't coded in close all. No, I want to close all. I haven't coded in MATLAB in a while, so I might be a little slow. So here in the inertia calculation, what I need to do is I need to move this to like inertia of satellite, okay? And then before I compute the inverse, I need to compute the inertia of the reaction wheels, okay? And so I need a mass of my reaction wheel, and so I guess I should go to Blue Canyon to pull these out. I'm gonna pause and pull up Blue Canyon real quick. Okay, folks, I was able to go to Blue Canyon, and just because those are the reaction wheels I'm most familiar with, and I downloaded the data sheet because the website has like some crazy animation on it, and like my computer is pretty old and only has 7 gigs of RAM, and I'm already topped out at 5.7. So, or not topped out, but I'm about to be. Anyway, I digress. Let's go with let's see, what's the size of the CubeSAT? The CubeSat's 2.6 kilograms. So if we're gonna use 3 reaction wheels. So if you use 3 of these, 0.25 times 3 is like 0.75. That's probably too big. Let's go with the RWP 15s. So we're gonna use all the data from this reaction wheel here, okay? So the mass of the reaction wheel is 0.13 kilograms. And then the volume is 42 by 42 by 19. So if I go back to my equations, there's a radius and a height. And so I'm assuming from that data sheet that the radius is 42 millimeters and the height is 19. So I'm going to say that the radius of the reaction wheel is 42 millimeters. the height of the reaction wheel is 19 millimeters, okay? So I divide by 1,000, obviously. According to my equations, that's everything I need to build up the reaction wheel in the reaction wheel frame. So the inertia of the reaction wheel in the reaction wheel frame is, can I factor that? I can factor out an M. Let's do that. So I'm going to factor out an M reaction wheel, and it's going to be 1/12 times the radius squared, and then 0, 0, and then 0, and then now it's MR, which is factored out, it's 1/2, right? Yeah, no, 1/12, I'm sorry. So the first one is 1/2, whoops. The second one is 1/12 times the, ooh, this is interesting, 3 times the radius squared plus the height squared. And I probably pulled that equation from Wikipedia. Then 0, 0, and then I kind of just want to pull this out and call this like, I don't know, I disk is equal to that, and put I disk in here, and then I disk over here, because that's basically the radius of the reaction wheel, okay? Then I need to compute this transformation matrix here. Now, in order to do that, I need to point out where the unit vectors of the reaction wheels are. So I'm going to have 3 reaction wheels. So we need to figure out the orientation of reaction wheel, okay? So that's N1 is 1, 0, 0, so that means it's pointing along the x-axis. N2 is 0, 1, 0, so that's pointing along the y-axis. And then N3 is 0, 0, 1, so that means it's pointing around down the z-axis. So then I need to make a T1 transformation matrix. So this is where things are going to get kind of weird. Let's go back to the table of contents, and somewhere here, this is what I want. I want screw rotation. So it is often useful to extract Euler angles from a unit vector. That's not quite what I want. I want to be able, and maybe I don't have, I might have to look this up. Give me 1 second. Okay, folks, so I went through my GitHub, and I found a function called rscrew. And basically what I do is I give the function an n hat, a unit vector in 3D space, and then I use these 2 equations to extract the pitch and yaw. So vectors only have 2 degrees of freedom. And then what I do is I take, I assume that the roll angle of that vector is 0, obviously, and then I take those 2 vectors and I rotate it into, I use the R1, 2, 3. So what I'm going to do is, instead of like, you know, what is it called? Instead of like adding this to the path, I'm just going to include this in the ADCS seminar series. So I'm going to create a new function and throw it in here and call it rscrew and just name it rscrew.m. And then I just noticed there's a function in there called TIB. So we need to see if that exists. Yeah, so it's called TIB. And so what we need to do is we need to call TIB instead, like that. And I think that'll work. So when we go back to the inertia now, I can say T1 is R screw of N1, and then T2 is R screw of N2, and then T3 is R screw of N3. Now, what I'd like to do is I'd kind of like to put this in debug mode because, oh wait, actually, I need to grab one more equation, and that is the equation where I rotate from the inertial frame of the reaction wheel to the body frame of the satellite. And so that should be here in the reaction wheel model. So I need to do a T transpose times I times T. So if I do that right, that means my I R1b, so that's the inertia of the first reaction wheel in the body frame of the satellite, is equal to T1 transpose times IRR times T1. And then TR2b is T2 transpose times IRR times T2. And then TR3b is T3 transpose times IRR times T3. Okay, and this is where I want to run this in debug mode. So I'm going to hit F5. I put a breakpoint in there. It didn't like it. It said H is not defined, of course, because H is HR. Okay. Run it again. Now we have a breakpoint. Okay, so the inertia of the reaction wheel in the reaction wheel frame is 0.11 on the we're assuming the disk looks like this, okay? And so T1 should just be the identity matrix. So then IR1B should just be the same because that's along the x-axis. Now, when we take the reaction wheel for the y-axis and rotate it this way, now my y-axis should be where the x is, and then my x and z should be different. So if I got this right, my y-axis, yep, is on the, wait, is that right? 0.06, 0.06. So yeah, so my x and z now are this way, or sorry, this way and this way. And then for TR3B, we're going to take the disk and rotate it that way. So that means that the z-axis should be the 0.11. And let's see if that's right. And there we go. Okay, so then I am satisfied with this orientation of the reaction wheel. Let's see. I don't want three. See, a lot of people ask me why I do 3 comments, because one comment just is like not enough. Like, I don't know, maybe I'm ADD or something. I just need to hit like a couple times. And then like 2 comments makes this like block comment business that I hate. So I just do 3 comments. Okay, it's just makes my life easier. So this is transformation from reaction wheel frame to body frame of satellite. Okay, and then this is compute inertia of reaction wheel in body frame of satellite. Okay, so now according to this equation then, okay, so I don't know if I want to do this. I'm going to assume that the reaction wheels are all at the center of mass. I don't, you know what, fine. Let's move the reaction wheels a bit from the CG. Okay, let's just do this right. So R1, let's see, the size of the CubeSAT is probably 10. So I'm gonna say it's 1 millimeter along the x-axis. I'm gonna assume R2 is 1 millimeter. This is ridiculous. Obviously, it's probably more like 4. I'm gonna say 4 millimeters, and then R3. Well, actually, if you think about it, the CubeSAT is what, 100 millimeters? So you can probably, let's say 20. Let's say 20 millimeters, that's fine. And R3 is 20 millimeters along the z-axis. Okay, fine. And then when we use this equation, we say we take the mass of the reaction wheel times the skew symmetric. Do I have a skew function in here? Skew. I have R screw. I do not have skew. So we need to go grab the, oh, wait, how do I do it? How do I do it in the satellite routine? Because I got to do, I use the cross function, but you can't do that. You can't do that when you're using this operator. So I've got to go find that. I think it's just called skew. Blast. Okay, maybe it's not in aerospace. Maybe it's in MATLAB. Sometimes it's just in here. Haha. Okay, so we're just going to copy this. I wrote this in 2015 apparently. That was a long time ago. And then we're going to, I know I'm like basically like rewriting functions that exist elsewhere in my repos, but a lot of people are have started to complain. They're like, where's this function? Where's that function? So I'm just going to kind of like put everything in one spot. So if you go to the ADCS seminar series after watching this video and download it, it should just work right off the cuff, okay? That's an analogy for working right away. All right, so this is compute the inertia of the reaction wheel in the body frame in reference to the CG of the satellite. Now, here's where things get weird, okay? If you add a reaction wheel, you're adding mass, which means you're shifting the CG, okay? I'm assuming that you know the composite CG of the entire thing, okay? Just pointing that out there. And oh, by the way, this is the mass of the satellite, and this is the inertia of the satellite. At the end of the day, all the way down here, we need to add everything up. I'm assuming that the total mass is the mass of the satellite plus 3 times the mass of the reaction wheels, okay? So that's the mass. The inertia is going to be the inertia of the satellite plus, and then that's where we grab this equation. You just grab the inertias all together. So we'll leave that with an error for now. But now we need to compute the inertia of the reaction wheels in the body frame in reference to the CG of the satellite, which means we need to use the parallel axis theorem. Okay, so we're going to say IR1 body frame CG is equal to, and it's IR1B plus the mass of the reaction wheel times that skew function, R1, transpose times skew of R1, okay? And then to speed this up, because this is going to take time, I'm going to call SR1 equal the skew of that, and that way I can just do SR1 transpose SR1, okay? And then I'm going to copy this 3 times. I don't know how much this actually matters, but I'm trying to be completely accurate here for you. Reaction wheel model. This is why I didn't want to do the reaction wheel model for a really long time, because this is just really hard to do. There's a lot of bells and whistles. We haven't even gotten to the control routine. Right now, we're just adding up the inertias. So then I should just do R1 B CG, IR2 CG, B CG, plus IR3 B CG, okay? So that's mass and inertia, and then we invert the matrix. And we're done for now, okay? So let's see, we have a typo in here. Why does it not like this? Okay, I don't know what Hermitian means. I'm not really good at linear algebra, but I'm gonna just listen to MATLAB because it's the matrix laboratory and they know what's up. All right, so let's see if that worked. So IR2B is undefined. Help me find it. IR2B. Oh, I put a T in here. Okay, so that function works. So if we run main, main does not look right. Line 83. What did I do on line 83? Oh, I messed. There we go. I must have accidentally put a typo in there. Okay, so the function works. Okay, so we have the inertias. Okay, and the simulation still runs, and it looks almost identical because barely anything changed. Clear, CLC, close all. Okay, I'm gonna make a function called purge. Clear, CLC, close all. I'm gonna call this purge. That way I can just type in purge whenever I want to just close everything. Okay, so now we need to edit the total angular momentum, okay? So the angular momentum, according to that equation there, oops, I don't want that. See down here, I have rotational dynamics, right? But what I need to do is I need to compute the total angular momentum, right? Well, I'm trying to think, do I need... See, I'm wondering if all of this inertia stuff should get moved. Yeah, I kind of do. So I'm going to make a function called reaction wheel parameters, okay? And I'm going to say reaction wheel params.m, okay? And I'm going to move, so in the inertia, I'm going to move this, okay, over to here. Boom, and then I'm going to move, and I'm going to call, obviously, call the reaction wheel params, reaction wheel params, because I'm going to use those parameters elsewhere. Here's the orientation of the reaction wheel. These never change. See, here's the thing. These never change. That's fine. If I need those T1s elsewhere, I'll put them in there. I'll move them over. And then these ones. Okay. So everything in here is a parameter of the reaction wheel, and everything in here is used to compute the inertia. Okay. Now, see, yeah, I do. See, I need the angular velocity of the reaction wheel. I also need the orientation, which I have that in here. Here's the orientation, but I also need this vector here, I B. I need both of those, okay? And not only that, I need the inertia of the satellite. So that means the inertia of the satellite needs to be a global. So I think I have here MI. I need IS. I need the inertia of the satellite to be a global. In here, I need I and IS, okay? All right, so, So when I'm computing the total angular momentum, I actually need the inertia of the satellite times PQR plus I need the inertia of the reaction wheel IR1 CG times, that's a 3 by 3, times a vector. So I need, see, okay, I can't do this yet. I'm going to comment this out. Well, I can't comment it out. I'm going to leave this as is, I times PQR, and I'm going to comment this out. This is what I want to do. I want to do angular velocity of the first reaction wheel times N1 plus IR1BCG times W2, the angular velocity of the second reaction wheel times N2, plus IR2BCG times W3 times N3. And the only things that don't exist are these. And so if I call, this is where things get weird. So all of this actually needs to be in the reaction wheel parameters, because unfortunately, in order to, I need to close one of these. I don't think I need TIB anymore, or skew, or purge. I don't need R screw either. I do need this one. So I need to call in the satellite routine. Well, see, the satellite routine is going to call the inertia, right? Isn't that somewhere? Or is it just a global? It's just a global. So over here, because they're assuming it doesn't change. So over here, they call the inertia, and it doesn't change. The inertia calls the reaction wheel parameters. And the reaction wheel parameters computes all of this, which is a constant. It doesn't change. So you only need to compute it once. So these IR1BCGs need to be globals. So IR1BCG, IR2BCG, IR3BCG, and then I need to copy that and make that a global in the satellite routine and throw that up here so that, and I know it's yelling at me because I don't use it, but eventually I'm going to uncomment this line of code and have it work. Now, how do we get the angular velocity of the reaction wheels? Well, we actually need to include it as a state, okay? So this is where things get even more nasty, okay? So in here, in the initial conditions, I need a W10, a W20, a W30. And these are the initial conditions of my reaction wheels. And that's W10, I'm going to assume is 0, W20 is 0, W30 is 0, okay? So now my state vector is 3 variables longer. I think that will be fine. This should compute all okay. This should compute all okay. I don't need to save the signal. Yeah, see, the current's not a state. That's why I had to save that. But the omega 1, 2, 3, these are the reaction wheel values. That should be 14, 15, and 16. And so I should just be able to plot the angular velocity of the reaction wheels. I don't know why I haven't been using freaking shorthand. Fig 7 is figure, set Fig 7, color white, and then plot. I think I can just do W123, I believe. Just increase the line width to 2. Throw a grid on there, throw an X label on there, throw a Y label on there. And this is angular velocity of reaction wheels, radians per second. And that should work. Oh, nope, no it won't, because in the satellite routine, I need omega 1, 2, 3 is state of 14 to 16, okay? And then down here, I need to add the total angular momentum. So I'm gonna pull that out. So that's the total angular momentum. This inverse I is the total inertia. Omega 1 is W123 of 1. W2 is W123 of 2. And then W3 is W123 of 3. And then in the derivatives vector, I need a W123 dot. So in addition to the rotational dynamics, up here in the controller, I need the controller eventually to output the reaction wheel torques. And we're not there yet, but basically what I'm just for now, I'm going to assume that the reaction wheel dot is 0, just to make sure this works. Undefined variable N1. I didn't make that a global. So in here, I also need to make N1, N2, N3 globals. And then in the satellite routine, make N1, N2, N3 globals. And then this is scaring me. IR3BCG, IR3BCG. Oh, IR2BCG. So 1, 1, 1, 2, 2, 2, 3, 3, 3. All right, we're good. We're golden. This is going to probably have a ton of bugs in it, folks. So just FYI when you download this. Hopefully we'll get something. Okay, so here's the satellite, 500 seconds. Then magnetic field, no change. Total magnetic field, no change. Euler angles, no change. Angular velocity, no change. Current, no change. Total current, no change. Angular velocity of the reaction wheels, 0. Sweet. Okay, so now we need to start running some tests. So first thing we're going to do is we're going to make the satellite not spin. Okay, so we're going to make it not spin. I'm going to throw a 0 in there and a 0 in there. And now what we need to do is we need to edit the controller. So the controller needs to output the current and the reaction wheel torques. Okay, now I'm going to set the current to 0 so that the magnetic torquers are off. Okay, so this is the B dot controller here. And then here is the reaction wheel controller, okay? What you need to do, it's not torques, it's reaction wheel alphas. It's the angular velocity of the reaction wheels. For now, I'm going to say that the angular velocity alphas are 0, 0, 0, okay? Now, I need to go to my reaction wheel model. The total torque placed on the vehicle is equal to the inertia of the reaction wheel times the angular velocity times that unit vector n, okay? So if I spin a reaction wheel, I should see a torque applied to the satellite, okay? So let's make RW alpha a constant, 1, and then in the satellite dynamics, this is where I need to here's W123 dot. Basically, the derivative is just that. It's the reaction wheel alphas. The derivative of angular velocity is angular acceleration, so it's just RWP alphas. That's it. Now, there is an issue here. If I need to say 4. 4I dx is 1 to 3, okay, and if W123 of I dx, the absolute value, is greater than the max speed. Now, this is where the datasheet comes in handy. It does not say what the maximum speed is. I'm going to assume it's 8,000 RPM. So we need to put that in the reaction wheel params. So we need maximum speed, okay? I'm going to assume the RPM is 8,000 revs per minute, okay? So then max speed in radians per second, so you have rev on top, so you need 1 rev on bottom is 2 pi radians. And then you have minute on the bottom. I'm going to pause for this ambulance. Okay, so then you have RPM, so you have rev on top, and then you want radians on top, so you put rev on bottom. So 1 rev is 2 pi radians, and then you've got minute on bottom, so you've got minute on top, and you want seconds on bottom, so 1 minute is 60 seconds, so it's RPM times 2 pi over 60, okay? So, and then I guess I need to make that a global as well. So I'm going to throw a global max speed, and then in the satellite routine, I'm going to throw at the top a, oh, actually, I just need it in the control block. So, no, I need it in the dynamics. Main, satellite, yeah. So I'll put it max speed, okay? So if the absolute value of one of the reaction wheels is greater than that max speed, then W123 dot of IDX is just 0. The reaction wheel cannot spin any faster, okay? Otherwise, W123 dot IDX is equal to the alphas, and that's that. So that should spin up. It's saying that it changes size. So I need to do 123 dot is 0, 0, 0. That way it allocates it. And then it looks like I spelled alphas wrong. RW, oh yeah, raw alphas are W alphas. Okay, so that's the angular acceleration of the reaction wheels. And in the control block, I am sending that command. There's something else that I'm missing here. So in the data sheet, you have a maximum torque that you can apply, okay? And that torque is equal to the inertia of the disk. No, it's equal to, if you take torque divided by inertia, you get maximum angular acceleration. So what I need to do is compute in here in the reaction wheel params. I need a maximum torque, and I need the max torque to equal 0.004. Okay, and that is in Newton meters. Yes. So then in the satellite dynamics again, when we command this thing to accelerate, if the absolute value of the reaction wheel alphas, IDX, is greater than the, what do we want to say? So we have the max torque here. So we want the inertia of the disk. So we want IR111. So I need IRR and max torque to be a global. Should I just do max angular velocity? I feel like that would make my life a lot easier. So there's max torque. Let's compute maximum angular acceleration. So max alpha is the max torque divided by IRR11. So that's saying take the maximum torque in Newton meters divided by kilogram meters squared, and you get radians per second squared. So that's the maximum alpha. And I want that to be a global in here, max alpha. What is it saying here? That's fine. I mean, maybe there's a bug, maybe there's not. I don't want to sit here and debug unless something looks totally wrong. Max alpha, okay? So then down here, I can say, if the absolute value of the reaction wheel alphas is greater than max alpha, then I want you to set the alphas of IDX equal to the sine of the reaction wheel alphas IDX times that max alpha. So there's two checks. So first, if the reaction wheel is spinning too fast, you can't spin it any faster. If you're trying to accelerate it too quickly, you won't be able to. Okay, so now with the control turned on with a 1, we should see the reaction wheel increase in speed. The satellite should stay the same because I haven't included the torque, but it should spin up. So let's see if that happens. Okay, so there's that. Magnetic field is changing, fine. Norm of magnetic field, fine. Euler angles are 0, does that make sense? Angular velocity is, they're all zeros, it's just there's noise in there, that's fine. The current is 0, that's good. Total current, that's good. Angular velocity of the reaction wheels, it didn't work. Okay, so we got to put this in debug mode to see what's going on. So I'm going to throw a debug point in here, throw a main. So I'm going to hit step, reaction wheel alphas is 1, 0, 0. I'm going to come over to here. I'm going to hit Oh dear. Did I crash my computer? What's going on? Did I crash MATLAB? Oh dear. I'm going to pause. I'll come back. Okay, folks, we're back. Reaction wheel alphas is 1, 0, 0. We are then stepping through. The W123 is 0, 0, 0. So it's not greater than that maximum speed. And the max alpha is 34, and the reaction wheel alpha is 1. So that's not true either. Oh. Duh. I put the end in the wrong spot. So I want an end. I still need to do this in here. Okay. Now that we fixed that bug, let's go ahead and turn the satellite. So here's LMN magnetorquers. I want LMN now. And I want total moments to be LMN equal to LMN magtorquers plus LMN reaction wheels. Okay? And then, so let's move the magnetorquer model up to here. Okay, and then the reaction wheel model will be here. So the LMN reaction wheels is going to be equal to, and I have to go back to the equation for this. It is the, IR1 BCG, right? Is it BCG? IRIB. Okay, so we need to be careful. It's the one that is not at the CG because that doesn't translate. So it's not IR1B CG, it's IR1B. IR1B, yeah, because you're just spinning the disk. You're not spinning. If I was using the IR1B CG, it would be like spinning the reaction wheel around the center of mass, but you're only spinning the reaction wheel around its center of mass. So that means, unfortunately, we need to make IR1B and IR2B and IR3B globals. So we're going to grab those, copy, throw it over to satellite, make those globals. Okay. And then, so we do IR1B times the reaction wheel, R1, 2, 3, the angular velocity, 1, times N1. And then I add IR2B times W1, 2, 3 of 2 times N2 plus IR3B times W1, 2, 3, 3 times N3. Oh dear. Okay, so now when we run this, the reaction wheel should increase in velocity, and the satellite should also turn the other way. Blast. I have a breakpoint. Continue. Everybody pray. It's Yuletide, everybody. Come on. Give it to me. We are waiting for plots. Good. Oh boy, we broke something. That doesn't look good. Well, it's possible everything's fine. I just, that reaction wheel is just spinning a lot. I actually think it's working. Okay? So let's add a PID controller. Okay, so I know what you're thinking. You have 3 reaction wheels on 3 axes. You use each one to control each axis. Dr. C, is it possible to have reaction wheels at alternate axes control the whole satellite with some linear algebra? The answer is yes. And I don't want to do it in this video because I'm tired. I don't know how long the video is already, but it feels like it's a long time. So let's just assume for the moment that N1 is along the x-axis, okay? N2 is y, and N3 is z, okay? Let's just, for the sake of the argument, assume that that's true, okay? I'm also going to assume that phi command is 0, theta command is 0, psi command is 0, and, oh dear. Okay, we are not going to do this video. P command is 0. Here's the problem. I have a magnetometer, which measures magnetic field, and I have a rate gyro, which measures angular velocity. If I wanted to command phi, theta, and psi, I would need a Startracker, and I would have to introduce a new sensor with new sensor noise. That is for another video. I got a bunch of requests for reaction wheels, and that's why I'm making this video. If you guys really, 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 really want a Startracker sensor in here, I will make another video and add a Startracker. And then if you really, really, really want direction control for the reaction wheels, I will also add that in here, and I will make that a separate video. If you then want reaction wheel control with reaction wheels that are not pointed on the principal axes, post in the comments again, and I will make another video. But for now, P command is 0, Q command is 0, and R command is 0, and we are just going to detumble the satellite, okay? So, RWP alphas. Actually, I'm going to do PQR command is, I'm going to make this real easy, 0, 0, 0, okay? And I'm going to say that the gain of the reaction wheel is 1, 0, 1, 1, 1, no, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm going to make that a negative sign, and I'm going to make the RW alphas equal to KRW times the difference between the PQR command and the PQR nav. Now, if I have my signs right, oh wait, everything's 0. I need to make the satellite spin. Yeah, this isn't going to do anything. Oh, it still blew up. Which it means my signs are wrong. Yeah, because that shouldn't have happened. Let me get rid of this minus sign. When in doubt, change the sign of your portional controller. Okay, so nothing should happen. Like, nothing should blow up. Let's just... That looks like it's just like... Oh! So the reaction wheels are moving, duh, because there's noise in the angular velocity sensor. Yeah, of course. So let's cause this whole thing to spin. All right. So let's go to main and let's make the reaction wheels spins. Right. So let's make them have some initial angular velocity, and let's see if the reaction wheels can spin up and bring that down. And hopefully this will work, and then we'll be done. We can call this video done. Merry Christmas, or Yuletide, or Hanukkah. I don't know, I'm trying not to sound like super American, you know. This isn't working very well. Maybe the gain's too small. Possibly the gain's too small. Let's do a couple things. Let's jack up the gain, and then let's increase the, and get rid of sensor errors. So we're going to jack up the gain, get rid of sensor errors, and see if this is still working. So satellite, sensor params, mag scale. Okay, so angle bias. So we're going to throw this to 0, and this guy to 0. So we have no sensor errors. Ooh, and we're also going to update every second, so that we're not updating every 5 seconds. And then we are also going to jack up the gain. So in the controller, I'm going to multiply by 10. Okay, and run it again. So we have reduced. We've removed sensor errors. We're updating every second, same as a time step, and we increased the gain. And so let's see if that worked. No, it looks like we're still going. Huh. I wonder if I have a bug in my, like, could be a bug anywhere. Let me change the sign one more time and see if that's it. If it's not it, I'll go off camera and I'll figure it out and I'll come back. Okay, let's see. If not, I'm going to go off camera and I'll tell you what I did to fix it. No, okay, so that went unstable. Okay, so I'm going to go off camera and I'll tell you what I did to fix it. Okay, folks, I figured it out, and unfortunately it's no easy fix. So here's the problem. So if you're familiar with transfer functions, the transfer function of this system is 1 over s squared. And when you apply proportional control to it and you do a feedback controller, you basically have 2 poles at the origin. And when you increase your gain, you're basically doing derivative. You're doing derivative gain on it, actually, which like throws like an s in the numerator. But anyway, the bottom line is that you're basically applying proportional control to a double integrated system. And if you look at your tables from introductory controls, that system actually goes unstable. And so what's happening is that, again, I'm applying proportional control to a type 2 system, or really like derivative control to a type 2 system. It's kind of weird. And so what I need to do is I need to add in, unfortunately, I need to add in the Startracker measurement. And so I can add in the noise again. I mean, that's not really a big deal. I was hoping I didn't have to do this, but unfortunately it looks like my hands are tied. So I actually need a Ptp Nav to pop in here. And so over here in the input to the control routine, I need a Ptp Nav. And that means over here, I need to do a Ptp measured. And then the output of the navigation block is going to be a Ptp measured. And then over here, or sorry, Ptp nav. Oops. Ptp nav. And then over here, I'm going to do a Ptp measured over here. And then the input to the sensor block is going to be Ptp. So I think I have quaternions, is that right? Yeah, there's quaternions, and I think, do I have a routine to convert to quaternions, Euler angles to quaternions, or what about quaternions to Euler angles? And then that function just takes in Euler angles, is that right? Or quaternions, yeah, okay, cool. So in the satellite routine, what I'm gonna do is I'm gonna do Ptp is quaternions to Euler angles of Q0, 1, 2, 3, and that will convert to my Euler angles. And then in here, I'm going to send Ptp to the sensor block to give me my Ptp measured, which means I need to go into my sensor block. And here I need to do Ptp IDX is Ptp IDX plus, I'm going to say Euler bias plus Euler field, Euler noise. And then in my sensor params, I'm going to add Euler bias is, I don't know, in radians, let's say 2 degrees, 2 times pi over 180 is my bias, and then my Euler noise, I'm going to say is my Euler bias times 2 times rand minus 1, and that will give me my Euler noise and my Euler bias. Okay. Let's go back to the satellite routine. So my sensor block is good. Now I need my navigation filter. So if I open my navigation filter, this is going to give me a Ptp measured, and it's going to return a Ptp nav. It looks like I need a Ptp nav prev. And it looks like I need to do some Ptp nav prev is 0. It looks like I check if it's 0, and if it's 0, I just do the Ptp measured. Otherwise, it looks like I do a Ptp bias estimate. Oh yeah, I was trying to estimate the bias, and then I basically do a first order filter. Ptp nav is Ptp nav prev times Ptp measured, which is an input, minus Ptp bias estimate, which is just whatever. And then I say Ptp nav prev is Ptp nav. Now these Ptp nav prevs, I basically need to go through everywhere in the code and see where these are. So there's a Ptp nav prev, and it looks like I have to initialize that here. So this is, I guess this is like initialize nav filter, okay? And then I'd also like to save the measured, yeah. So these aren't state vectors, right? So I'd like to do like a Ptp measured is zeros length t out, comma 3. And then I guess like a Ptp nav is 0 times Ptp measured. Okay, and then over here when I like save everything, I guess I'd like to do save Ptp. So I'm going to have a Ptp measured IDX comma all is Ptp measured of like that. And it doesn't look like it's a global. So I'm going to need a Ptp measured and Ptp nav to be globals. That way I can throw them in here. Ptp nav IDX comma all is Ptp nav, like that. And then I can plot it. So when I plot it in the magnetic field, the norm, the Euler angles. So here I can do hold on, and it looks like I do. It looks like I do P1 is this with solid lines, and I do a hold on. P2 is plot T out Ptp measured times 180 over pi. That's in squares. That's the measured signal. And then P3 is, I forgot a semicolon, is T out, comma, Ptp nav times 180 over pi, and that's dash dashed, same thing, line width of 2. And then I grab the legend, and I think I can just grab the same legend. They're all the same. Alt-W, and then Alt-Y, throw in a semicolon. Do I have everything? Will this work? I don't know. I don't know about you, but I lost my train of thought. Let's just see what happens. Okay, thank you. Let's see. So the first thing is that it didn't like the Q0, 1, 2, 3 in line 7. So in the main routine, let's run it and let's see what the breakpoint is. So Q0, 1, 2, 3 is a column vector. So I guess I need to put in here and say, like, if size of Q, is size a function? Oops, I'm sorry, you guys. I just, like, size of inverse I is a variable. Size of inverse I. And then if I do A of 1, okay. So, I'm sorry, you guys. So if size of Q3 equals 3, 4, 1, let's do this. S is size of Q0. I'm going to say if S of 1 equals 4 and S of 2, oh, there's no and, you have to do ampersand, sorry, is 1, then do Q0, 1, 2, 3 equals Q0, 1, 2, 3 transpose. All right, let's see if that works. Okay. Q0, 1, 2, 3. Too many arguments, input arguments to sensor. Sensor is taking in the magnetic field, the angular velocity, and the Euler angles. And the sensor routine is here. It's supposed to take Ptp. Okay, so that should work now. Too many input arguments, too many output arguments. So Ptp measured back to the sensor block is supposed to output Ptp. Main. Undefined function or variable Ptp nav. So let's see what's going on there. So Ptp measured, that's here. Ptp measured is here. It's not a global. Ptp measured. Ptp nav prev. That's probably why. It still doesn't like it. Ptp. It is Ptp nav. Ptp nav is a global variable. I didn't mean main. Okay, so Ptp nav. Oh dear, it is a 3x3. That is not good. What's happening? So we need a breakpoint. Oh my gosh, I broke the crap out of this, you guys. This is, man, reaction wheels, holy mackerel. Okay, so that's a 1x3. What? Oh, of course. I need to put a, nope. That's a 0, 0. Okay, step, Ptp measured, some noise, Ptp measured, then Ptp nav, good. Okay, so quit debugging, get rid of the debug point. Let's run it. The system should still go unstable because the reaction wheel is trying to control the whole thing. But at least it should work. So in the Euler angles, that's the angular velocity of the reaction wheels. That's the instability there. There we go. Boom. Yeah, sweet. Okay, cool. So we are measuring once a second and we're filtering. Haha. Okay. Startracker is now working. Thank goodness. Okay, so now we can finally send Ptp nav here. And I want Ptp command to be 0, 0. I want even the command to be 0, 0, 0. And then I'm going to have kd be that, and then kp be, let's make this easier. I of 3 times 20. Let's make that 5. And then we're going to have kp times Ptp command minus Ptp. plus KD PQR command minus PQR nav, and this is Ptp Nav, not. All right, everybody. Let's hope this works. Let's stabilize our satellite. Oh my goodness, oh my goodness, oh my goodness. Did it work? Oh dear. I mean, yeah. There's noise in the yeah. There's still noise. Let's try to compartmentalize the system. Let's get rid of what I mean by compartmentalize is like let's get rid of the errors. So no error no errors in the angular velocity and no errors in the Euler angles. And let's see if that will if it works perfectly. And it's still, man. It shouldn't. Oh. Okay, I guess I'm going to come back. I thought the Startracker was the issue. I'll come back. Okay, folks, there was a lot that was broken here. It turns out that I didn't actually need the Startrackers to slow the thing down, and I'll talk about that in a second. Let me just talk about the changes that I made to the sim. So the first thing that I'm doing is I'm simulating for an entire orbit, so that's like 5,700 seconds. I also am saving the reaction wheel acceleration so I can actually plot them. I also am calling the derivatives routine once outside the RK4 loop just to initialize a bunch of variables. And then right when I enter the loop, I save everything. And then I do my RK4 call. I had that backwards before. I'm now plotting everything, including the current and the acceleration of the reaction wheel, so we can see what that is. Nothing changed in the sensor program. All the sensor errors are currently on. I'm updating it once a second right now. I could probably change that, but that's fine for now. In the satellite routine, I don't think there were a couple things I changed here. These are where the big things come in. Okay, so for one, this equation here, if I go back to my torque model, I need to grab the inertia of the reaction wheel about the center of mass of the reaction wheel in the body frame of the satellite times the angular acceleration of the reaction wheel times the unit vector. And I had the angular velocity placed here. So I was actually trying to control a type 3 system with derivative gain. And it turns out that when you put the angular velocity in there correctly, you're actually controlling a type 2 system, which is totally correct and able to do. I guess I was trying to reason through it, and I reasoned through it incorrectly. Then the other thing was that the inertias were wrong, so I had to put that in. The other thing that was wrong is that I realized that when you apply a torque to the reaction wheel spins one way, but it causes the satellite to spin the other way. And so whatever angular acceleration is applied to the reaction wheel, you need to apply the negative to the actual satellite so that it spins the other way. So I had a lot of minus signs in a lot of weird places that were incorrect. I was also adding the total angular momentum incorrectly. So I was using the CG of the satellite rather than the CG of the reaction wheel. So you're probably wondering, like, when do you use the CG of the satellite as the inertia point? And that's only when you're computing the total inertia. So when you're adding all the inertias together, that's when you add up the whole thing and you add the parallel axis theorem. But when you are computing the torque applied and the total angular momentum, you only use the inertia of the reaction wheel. And actually, now that I'm thinking about it, I think this is actually supposed to be I, right? No, that says IB. I feel like that's wrong, though, because the whole thing is, well, unless you assume that, yeah, I see. It just depends on what you're assuming is your reference frame. So I'm going to leave it there. I don't think it's going to make too much of a difference. So then in the control law, what I did was I added a two-phase controller. So what I did was I went ahead and lowered the gain of the B dot controller down to 67,200, and so the B dot controller is always on. And then what I said is if the sum of the angular velocity from the rate gyro is less than 0.1, kick on the reaction wheels. And then right now, the only thing that it's doing is just detumbling. And so if you look at the simulation, you can see it does one orbit, so that's pretty standard. But then you can start to see some neat plots here. So here is the angular velocity. So you can tell here that the angular velocity is a certain value, and it's slow. It's hard to see, but it is decaying. And at some point, it decays lower than 0.1, and then the reaction wheels kick in. And so if you sort of run over to, say, this plot here, here's the angular acceleration of the reaction wheels. So they're, going, and then boom, they turn on, kick in, and then cause the angular velocity of the satellite to decline. And then if you look at the current, the current in the magnetorquers is like saturated, and then once the reaction wheels lower the angular velocity, the current basically goes down to 0. And you could probably turn off the magnetorquers if you wanted to, but it is what it is. The other neat thing is that the Euler angles are, spinning, and then they pretty much go constant. They would be constant if it wasn't for the noise in the system, but obviously there is a little bit of noise there. Here's the current in all three axes. We already looked at that. We kind of looked at that plot already. And then here is the angular velocity of the reaction wheels. So they're not spinning, and then they kick on, and then boom, they shoot up. And this is another interesting point, by the way, is that the satellite is not moving, right? The satellite angular velocity is 0, but the angular velocity of the reaction wheels is non-zero. They're still spinning. And so you would have to code in like a desaturation scheme to basically spin down your reaction wheels, and then use your magnetorquers to remove momentum from your reaction wheels. In this time, I wasn't able to get the pointing control of the reaction wheels coded. I think this video is long enough as it is, and I think I've sort of overstayed my welcome here. So if you enjoyed this video, post in the comments. I'm going to push this code as soon as I'm done here, and so you'll be able to download this code. So it'll have B dot controller and magnetorquers, and then B dot control with magnetorquers, and then derivative control with reaction wheels. And then I guess in a later video, I don't know when I'm going to get to it, but I'll probably do a video on pointing control with reaction wheels, and then I guess another one would be desaturation of the reaction wheels, and then a third one would be controlling a satellite with reaction wheels not on principal axes. But that's going to take a lot of time. I mean, as you can see with this video, this took a while to get to work, but hopefully you guys can run with this and play with it, and then let me know if you have any questions.